Hello, this is our final video on nonlinear pharmacokinetics. Woohoo! So let's get going. All right, so this is on recognizing and evaluating nonlinearities. So what you're going to do is compare what is observed to what is expected for a linear relationship. And for the most part, we expect most of the parameters to stay constant. We expect fraction unbound to remain constant. We expect enzyme activity to remain constant as concentrations increase. So as concentrations increase, it should not alter binding or enzyme activity or half-life or K, fraction amount of tissue. Am I thinking of them all? So bioavailability and volume and clearance and your effect in the effect model should all remain concentration independent. In other words, as the concentration changes, you should not see a change in bioavailability, volume, or clearance. You will see a change in E, so that's probably doesn't fit there. And then when you see what happens, you should be able to consider what the possible mechanism is that causes it. So if the clearance is going up with increasing concentration, then you should be able to say, okay, so what could be causing that? Or if the clearance is going down with increasing concentration, or any of the other things that we just talked about. So you should be able to think about what could cause that. And most importantly, you need to make sure that you don't treat a nonlinear situation as if it were linear. Remember, when we have a linear situation, our CSS average is equal to bioavailable dose rate over clearance. And as long as there's there's linear pharmacokinetics, both the bioavailability and clearance should remain constant with changes in concentration. So if these two things remain constant, then CSS average and dose rate become proportional. So our dose rate, as our dose rate increases or decreases, our CSS average should increase or decrease proportionally. That would be linear, right? And we use that idea so that we can then say for linear drugs that dose rate 1 is to CSS average 1 as dose rate 2 is to CSS average 2. But if this is not the case, if bioavailability and or clearance are not linear, are non-linear, then we cannot use this equation. That's really the most important thing in this whole discussion, is to make sure that you don't use the assumption that you have linearity to make decisions. And that was when we very first talked about the very situation when we made a dose rate change with phenytoin. We assumed it was linear. The doctors assumed it was linear, and it is not. So you cannot use a proportion to make dosing regimen changes. Just like similarly, area under the curve is equal to bioavailable dose times clearance. Again, if the bioavailability and clearance are linear, which they are in most cases, then you can use this equation to make dose regimen changes. So dose 1 is as area under the curve 1, as is dose 2 under area under the curve 2, but that assumes that the bioavailability and clearance are linear. If either of those are not linear, then again, you cannot use this equation to make dose adjustments. Normally, as your dose or dose rate increase, your CSS average or area under the curve will increase proportionally. So you go along this middle line because this is linear kinetics. If you see that as your dose increases or dose rate increases, it's proportional for a bit and then it starts to flatten out. That's because there's nonlinear kinetics, either in the bioavailability or clearance of the drug. Same thing here. You could actually have the CSS average or area under the curve increase more than proportionally. So these are both nonlinear situations. So your bioavailability, volume, clearance, fraction amount in plasma, fraction amount in tissue intrinsic clearance of your tubular secretion, half-life, and K should all remain concentration independent. So as the concentration increases, you would expect to see no change in any of these. That's linear kinetics. Of course, they could increase or decrease with increase in concentration, and then these would be nonlinear. So how do you actually dose? If we can't use these equations here that we like using, oops, we can't use these equations, how do we make our dosing adjustments? Well, that's for a discussion for another time. So we'll discuss that in lab. Okay, thank you. See ya. Bye-bye.